I would like to thank you for participating. This will be a more technical presentation. Mr. Yalçın mentioned about the aviation industry. When we talk about composites, we think about aerospace and sports materials, etc.
Uygulaması da çok bahsi geçmeyen, son zamanlarda popülaritesi artan makine endüstrisi. Kısaca içerik olarak biraz kendimizden...
Well, let me talk about ourselves and then composite design process, composite production problems, and composite use in machinery sector, and its design and correction. And as a company, we were founded in 2010. We are headquartered in Istanbul, and we provide integrated solutions to the companies. We want to be the engineering partner. We have two operational areas. One is R&D and engineering solutions. The other one is renewable energy solutions. Today I will talk about R&D solutions. Well, we have lots of solutions for composite engineering. So a single device, a single software cannot be sufficient for composite. We have different geometries for different purposes. Therefore, we have different device needs for different purposes. And every device has specific features. So I can say that they are specified. There are 4 different items that I can talk about here: analysis and simulation softwares, design and production softwares, production and quality equipment, and the services, engineering services provided. NXCA, CAE, or hypervisor softwares can be mentioned for analysis and simulation. So we do the verification, optimization, and in certification of the components. These are the solutions we use. Design and production. Composite design and production process. Conventionally, they are different from each other.
Boyutlandırma aşamasında laminasyonlar, oryantasyonlara belli.
Of course, the orientations can be settled. Sometimes 3D designs are created. And there are different layers within the production, and technicians mostly control this. At the end of the work, there is a risk that you will have a totally different production than you designed. FiberSim, developed by Siemens, or Canvid or Syncrofit, are used as softwares. One of the other issues are the fiber machines, laser projection devices. These devices are important for aircraft or aviation industry. Composites are not like metals. You can use them locally to reinforce certain areas. So the technicians can lay the fabrics correctly, and without any damages. We can talk about ultrasonic systems. Force, a company from Denmark, is a facilitator here. They provide automation systems. Another company is robotic fiber lay down device. The composites are produced with using robots, and they are not used actively. In the future, in automotive industry, robots will use this actively, I think. And in terms of turning from metal to composite, converting from metal to composite, we give engineering solutions. Of course, the composite and sandwich structure design and optimization, finite elements analysis, vacuum infusion, RTM process simulation, and conversion from metal to composite, advanced composite material and production procedures are some of the areas we work on. Composite structure design. This is actually a little bit different than the other sectors. The material production and design are intertwined. For instance, when you are designing a metal, you pick a material, you look at the thickness and whether it's bendable or not bendable. In composite, you check whether it's dry or prepreg, whether it's continuous or interrupted, whether it's core. So there are different materials and different prepregs of the materials. And similarly, the processing, the production of these materials are diverse because composite material is a combination. The chemical materials and resins are combined. The combination rates, the molds used, and there are lots of different parameters I can say. And in terms of design, you can use any geometry, but if you are producing a tank, for instance, you need a different design geometry. If you are producing a wind turbine, for instance, you use infusion. For automotive makeup materials, we have the spraying methods, but all of them actually are intertwined and they shouldn't be separated. For composites, some common problems we might mention. Well, I think this is one of the biggest disadvantages. What are those? During production, well, let me put it another way. It's a labor-intensive production. It's true for aviation, for automotive, and for the other sectors. The fabric is flexible and it can crease when it's not handled properly. Waving, delamination might occur, and if the fiber is not wetted totally, there might be some dry points. Wrong curing and sandwich, face core separation, and microfiber creasing might happen. Of course, in order to have a profitable and high quality production, we need to locate it as fast as possible, and we have to use products which have been prepared before. Curing process in automotive sector, there is high volume of production. A steel plate is produced in a few seconds, maybe. They want the same speed for composites as well. Therefore, we are working on fast curing resins. It's less than 5 minutes now, but of course, it's not as fast as steel. In the times to follow, there will be lots of developments because there is high amount of investment. BMW for E series, they have the production time of 7-8 seconds for a plate. It is a cure system, therefore you can achieve a certain geometry you desire. Sometimes you can't because the material might shrink, and the single-sided fibers can change angle when even they are being carried. These are the challenges of composite production. Well, most of the producers here might say we have solved those issues. Another issue is strength. As you know, the composite materials have the biggest strength thanks to their fiber structure. When you are calculating that, you have to consider it. If you cannot produce it at the desired angle, for instance, you wanted it to be green, but if it is orange, that will lead to a loss of strength. Here on this graphic, for instance, the fiber orientation angle on the bottom side and the linear line is about elasticity ratio. Even in 10 degrees of difference, there is a high loss of strength or endurance. Therefore, lots of issues have to be pre-assessed before design and production. Another issue in fabric proplex systems, for instance, there might be some challenges on the red parts over here. Creasing might occur. You might have to take some precautions. Or if you start putting the fabric from here, there will be no creasing. Or if you change the material, although you have the same area starting point, it might create a problem because sometimes it is a combination of carbon with glass. Sometimes the composite ingredients are different. So here we start from the same point, and this is 45 degrees of lamination. The creasing might occur. But if you do it in another fashion, creasing might not occur. So it doesn't have to be just the same. With different materials, with different orientations, we might face different problems. Another issue, if we are laying it down, if it has a multi-axle fabric, some of the fabric, they are 3-layer ready to lay fabric. Some of them are okay, but for some of them, micro creasing might occur. What I'm trying to say over here, the solutions are available. One is automation for production, all ply cutter. You need to define what kind of a fabric, what kind of a ply do you want, and the automatic cutters give you the least waste and the best option, best solution, sorry. And you can use the laser indicators for your production. That will prevent wrong materials or wrong orientations, so you will solve the problems in advance. Another issue is about robotic systems. Pilot placing. The fibers are laid down, and fiber and the resin comes from different resources and just get together here with a curing system. They are combined. Here, the problems caused by the laying down will be prevented. What is another method to prevent these problems? Simulation. At all phases of design, simulation will be used in product development process. By the way, product development and R&D concepts are confused sometimes. Some people, some centers are R&D centers, but they're actually developing products. R&D are more scientific, and engineering products will be product development. Concept design to serial production. The four design and engineering works are undertaken, and verification and tests are undertaken, and then molds and auxiliary products are prepared, and you turn it into a serial production. But if you face a problem in production phase, that would make you to go back every step to the beginning and check the design and engineering, verification and test. So it creates certain costs, and the biggest cost will be late launch of the product, and that leads to a loss of income. Of course, in case of recalls of vehicles or cars, that will be a problem. With simulations, with analysis, with certain engineering approaches, you can achieve the desired quality. As I said before, in wind turbine production or in other sectors, in automotive sector, the composite materials are getting more and more common. And I think that they will be used more in the machinery sector. Energy consumption, energy efficiency is very much important today, and this increase will be even higher. Therefore, in this presentation, the machine systems and the composites, how to verify them will be talked on. In machinery sector, there are lots of applications. The robot arms, for instance, the robot producers try to achieve lighter products, hydraulic pistons, bombs, and the bridges, the carrier cars, shaft, and movement transmission organs will be the usage areas. Here, there is an issue. The static material will have static load, or in time the change will be minimum. But when it's a machinery sector, when it's a moving part, the load differs and the load increases in time. Of course, this leads to absorption, which is a very important issue. So if you have high absorption ratio with the products you produce, the vibrations will diminish soon. There are three different types of tubes compared here. I will just show you the two tubes. One is carbon, one is steel. The national frequency of the steel, it's more than 730. The carbon fiber is more than 1,400. The dynamic absorption, it's 0.025. In carbon, it's 0.003. So the vibration loads are absorbed more easily and faster. Similarly, when there is a load on it, what is the situation? If there is a load on tip of it, what happens? The natural frequencies do not change very much. Carbon fiber decreases from 500 to 300. There is that weight over here, and the steel has more dead weight than composite material. And of course, when you put an additional weight on the composite, the impact is a lot different. For instance, the steel is 1,000 kilogram, 1,000 kilogram. When you add 20 kilograms, it might not be a difference, but if it is 100 kilogram and if you add 30 kilograms to it, it will create a big difference. The moving parts, composite use for moving parts. Of course, there is an advantage here because it gets lighter. The energy consumption is decreased, and in order to decrease the energy consumption, you can use composite materials. The vibration performances increase. As I said before, damping factor can be adjusted and you can increase the vibration performance. Moreover, well, based on the prolongation and extension of the steel, the sensitivity problems might occur. For instance, there might be heat changes, temperature changes, and thermal prolongation will have an impact, different impact on the composite material and metal material. If you're working in high temperatures, the composites might get challenged, I can say. The composite pieces. How can we verify them? There are different methods, for instance, analytic methods. You can use the Excel devices or some devices we have learned from the books or with different softwares, and finite elements analysis. I will talk about the finite elements analysis. I will talk about that, and the flexible multiple particle dynamic analysis. Its important optimization could be iterative or numerical. When we are converting components from metal to composite, of course, we have to think and consider certain issues like critical loads or the operation speed, the impetus and jerk limits have to be detected, or bad case operation scenarios have to be worked on, and bad scenarios should consider the original structure and multiple particle dynamic analysis. Composite materials do not prefer sharp edges. Circular edges are preferred, or you can combine a few materials together. And composite lamination data should be formed to check rigidity and natural frequency analysis. By doing that, the iterative analysis and optimization can be checked. Similarly, steel and composite. We have to put them in the same simulation environment, and iterative checks have to be done. This is a rigidity impact by the production method. Here you can see there are different production methods, although the materials are same. How to produce the circle here? Like a chamomile, maybe, or like this one on the right-hand side. They show the same mode, but orientation is changing, therefore rigidity would change. This is all about a production process. Should I produce it as a single piece or a double piece? Finite elements analysis. I would like to talk about that in short. On the CAT analysis, we are breaking down the material into the smaller pieces, mathematically, I would say, and we define a solver, a finite elements solver here. When we do that, the deformation can be, and tension can be measured. There is a pre-processing, solution, and last processing. When we look at the monolithic composite structures, do I have enough time? This is, for instance, a multiple layer composite. It's called monolithic. Or if there is a core material in between, the height is increased, and it's called the sandwich composite structure. This is similar to a column calculation. BH cube will be 12, for instance, and we can increase the h, and we can get a system which is lighter but more rigid and more endurant. Here, for instance, a column or a built-in kitchenware can be produced using this method. Or vibration analysis, when we apply a differentiating load on it, we can predict what is to expect. The springing rigidity, for instance. We can see how much it's twisting. The sandwich model and monolithic models are compared here. There is a 0.20 in sandwich and it's 0.67 for monolithic model. The maximum tip twisting angle. Of course, the numerical methods or analytical methods can be used to calculate these differences or frequencies. natural frequencies. A material, even if nothing happens, we vibrate. Even the static materials have a resonance and we can calculate it. This is called natural frequency. In sandwich it's almost up to 58. In monolithic it's almost 40 hertz. Well, if we take this, put it on a bench, and when we put extra materials on it, when we add masses on it, the multi-frequencies and other factors might change. Here you can see the first four modes. Of course, the multiple particle dynamic analysis should be mentioned. These might be used in the machinery sector and automotive sector. There's a video here.
Tamam, çalıştı, tamam, çalıştı. Teşekkür ederim, sağ ol.
It is working. Thank you. This is a robot. Well, with the multiple particle analysis, it is mimicking how a particle is moving. You can calculate many things, and this is a robot that is moving on rail, and you can calculate the forces as well. What is the advantage here? In the machinery sector, a moving part can be simulated and its behavior can be analyzed. This is another example. The robot result was that all the parts were rigid. Here you can think that all of the parts are flexible. When the bench started working, it has got a vibration. It's exposed to vibration. And this robot here is following a crack here. But when moving, when maneuvering, or when stopping, it is exposed to certain forces and it vibrates, and sometimes desired geometry is not achieved. Here, you can see that the impetus changes on X and Y axis. If it is rigid, there is no difference in impetus change, but if it is flexible, it might face different speed changes and it might lead to fatigue on the material. Another example. It is not clear, but let me explain to you. A half circle movement. This is a movement just completing the half circle movement. If it is rigid, it can do the chore, but none of the materials in the nature is rigid. They are definitely have a certain flexibility. If it is rigid, it can do the chore. But if our bridge, this part, the composite part, is flexible, then and there are certain masses on it, by the way. Look at the tip over here, for instance. What kind of a movement is realized here? We have the desired movement here, and at the end of the simulation, what kind of a movement is realized? We can check the densities and tensions on it. When we put it in the graphic, it's a half circle. It's quite has a sharp movement. It cannot complete the chore, and it has a zigzag pattern. You can see it with the simulation, and afterwards certain optimization, iterative optimization can be realized, and you can fix it, and you can carry it to different points, I can say. Let me show it to you. Complete the half circle movement. And now it stops all of a sudden and starts to draw a straight line. And in such a situation, we improve our structure, we can achieve a lower rate of failure. Every machine works with a certain sensitivity, 10 micron, 20 microns, 50 microns. If we can foresee the micron rate, we can achieve the desired design. Of course, as I said, I've been trying to speak fast, but this is a very deep issue, and there can be different applications, and there might be different optimization parameters for composites. Here, I just try to inform you that such conversions are possible, and with simulations and foresight, we can realize it. In the machinery sector, we have a great and huge machinery sector in Turkey, and it's a growing sector. One of the targets is energy efficiency. The energy consumption is aimed to be decreased. The composites in this sector will be an important player and will be beneficial. Mr. Yalçın mentioned about the aviation industry. The product development process will be 10 plus years. An aircraft production, it can be a Boeing or it can be an Airbus. So they spent engineering effort for 10 years. In machinery sector, well, the advanced composites can be used. There are different applications and they can be used immediately. Well, of course, I'm not saying that we should give up on aviation. All the technologic innovations come from aviation and aerospace improvements. The mobile phones that we are holding in our phones, in our hands, etc. Everything actually occurred after the developments in the aerospace and aviation industry. So as a country, we have to follow it. We have to chase it. Unfortunately, we are not patient enough, but we need to be patient. We have to work without getting away from it. The previous speaker talked about the transportation, the aviation, and the passenger aircraft, but there's private jets as well. The private jets and the individual use of aircrafts are very much a big sector. It can be business jets or it can be the hobby like aviation vehicles. So we have to insist, we have to be persistent. Sometimes you might lose money, sometimes you might fail, but we have to be persistent. So there are different areas that can benefit from composite materials, like robot arms, the hydraulic pistons, the bombs, the moving parts of the components. And the production method is very much important. It should be assessed together with the material features. The moving parts will be advantageous if we use composite materials because it will get less heavy. It will get lighter, and the composite materials